Good morning, everyone. So first of all, I would like to thank the organizer of the workshop. I also would like to thank IPAM for the organization of the long program. I need to start, confessing that I'm not a computational physicist or chemist. I am actually more a machine learning guy. But I think this is the idea of IPAM, bringing people from different fields together and see, if we can make some collaborations. So actually, this work is motivated by a talk given by Alan Aspouri-Guzik last year. So there was a workshop about new deep learning techniques. So Alan came to the workshop. He gave a very inspiring talk. I think his title was something like, "Do androids dream of electric molecules?" So that was very inspiring for me. And I thought, I could do something because I work on a technique called, graph deep learning. And of course, molecules are graphs. So I try, to use what I know to work on the molecule generation task. So this is what I'm going to show you today. This is this work, and this is a joint work with Thomas Laurent. So the outline is simple. First, what I'm going to do is that I'm going to introduce graph convolutional neural networks in a general way. And then I will introduce a graph auto-encoder architecture for molecule generation. And I will conclude. Okay. So graph neural networks. So they are a class of neural network that are specialized to data that lie on graphs. Okay. So the question is, how do you design these architectures? So you need some properties. The first property you want your graph neural network to be invariant with respect to the indexing of your vertices. So a vertex has a spatial number 10, 100. You want your graph neural network to be independent of this because you don't want to do any graph matching. When you compare graph, you don't want to solve this problem, which is very hard, which is NP-hard. The second thing you want to do is that you want locality. We know locality. For example, if you do computer vision, this is very important. You want somehow to be, you only want to look at, the local neighbors first. So for this, it's easy. You just need to look at the neighbors of your vertex. So if you have a vertex I, you are interested, in the neighbors. So for example, these two vertices. Then you want to, you don't want to have too much parameters. So you would like to have some kind of convolution operation. So you have some weights, and you want to apply these weights, at different locations in your graph. So you want to do weight sharing. And finally, you want your graph neural network to be independent with respect to the size of your graph. Okay? So at the end of the day, the only equation you can do to represent, one vertex I is a function that we apply on your neighborhood. And the question is, what is this function? So it's basically what is the class of neural networks you want to apply to design these graph operations. So the first paper introduced by Scarcelli in 2009, basically they used the most natural neural network, which is a feed-forward, fully connected neural network, with what we call multi-layer perceptron. Okay, so this is the simplest model you can think about. And then, of course, you have more, you have like better neural network, like recurrent neural networks. So this class of neural network, they can analyze, long sequences independently of the size of the sequence. So people design a graph RNN, like a graph GRU, or graph LSTM, if you know LSTM in natural language processing. But the thing here is that the graph is completely arbitrary. So if you know LSTM, you know that to compute the representation, the embedding of the vertex I, you have a special structure in natural language processing. You know, it's a long sequence. It's basically a directed acyclic graph, okay? And for this special structure, you have an analytical expression to compute the representation of your vertex. Here, you don't have this, because the graph is completely arbitrary. And because of this, if you want to solve this kind of equation, you will need to use a fixed point iterative scheme. And so there is the question of convergence, existence, which probably is not possible. So what we do basically, we just iterate a little bit that. So we just do a few inner steps of this iterative scheme, and we take the solution as it is.
Are your sigmas the weights for your different
sigma? This one?
No. Yeah.
Sigma, it's a nonlinear activation, like ReLU, tangent hyperbolic, sigmoid, if you want. You need a little bit of nonlinearity in your system, and this is it. So another very powerful class of neural network is convolutional neural networks. So this is a very powerful class, for image processing for computer vision, and what we try to do with other people is to generalize convolutional neural networks to graphs. Okay, and this is very similar to the traditional ConvNet. So the idea is, if you want to get a representation of your vertex I, so this is layer L+1, so you're going to stack many layers. At the next layer, you're going to use the neighborhood, okay, of this vertex in the previous layer, and also you're going to use the same vertex here. So in an image, usually you have like a grid, okay? You have like a 3x3 grid around, and then you are going to use this 3x3 grid to construct a new feature. Okay, so it's just a generalization here. What we did, we used all the tricks that work very well in computer vision to design a powerful graph ConvNet, so graph convolutional neural networks. So for example, we use what we call residual connection, and also we introduce some gates inside the equation. And what you have here is something that, if you know image processing, is something which is basically, here you have a diffusion operations. Okay, you are going to diffuse on the graph some information. Okay, and here you have like an iterative scheme. This is like your time, t plus delta t from your current time t, and then you have your diffusion equation here. And what you have is something that is kind of peronomalic nonlinear diffusion process. So so in image processing, we use that to do image denoising. So if we have, noise in an image with on some homogeneous regions, we don't want, we just want to diffuse in these homogeneous regions. We want to do some averaging operation, but we don't want to diffuse across two different regions. We want to preserve edges. And this can be done, by using some anisotropic property here. Okay, so this is a kind of learnable nonlinear diffusion process that you can create on graph.
So by anisotropic, you mean it's not symmetric? By anisotropic, you mean it is not symmetric, or what do you mean?
It means that so if you don't have this, the only filter you can learn on graph are going to be isotropic. So if you look at the value of the filter in the neighborhood, they will all have the same value. Okay, but you don't want that. For example, if you're in a social graph, you know that some neighbors belong to a different community, so you don't want to treat, these neighbors in the same way that you would treat neighbors in the same community. You need some anisotropic information. The problem with graph is that you don't have any center, and you don't have any special direction, like up, down, left, and right. You don't have this. So you need to create some kind of anisotropy inside your graph. So this is one way to do it. For molecules, we have already this kind of anisotropy, because we have, for example, single, double, aromatic, all this kind of type of bonds. It's already some kind of anisotropy. But still, in a general graph, you want this kind of anisotropy, and you can learn this anisotropy with data. Yes?
I think part of the confusion, I'm assuming, was that are these graphs embedded in 2 or 3-dimensional space, and thus the edges are endowed with any kind of...
No, it's completely arbitrary. So you have a graph. This is the structure, between two nodes. And then you may have any feature, like 3D coordinates, charge, any feature you want. And the same also for your edge. You can have any kind of feature. It's really completely generic. And that's good in some sense, because it's super generic, but also you want something that is specialized to your domain expertise.
So there's no well-defined notion of direction from a node, but
exactly.
Isotropic, and when you say anisotropic, you just mean the neighborhood weights are not all
the same.
Okay.
Absolutely, yeah. Yeah, that's the thing with graph. Yeah.
Got it.
Another question? So yeah, you start.
Probably also related. So in your case, so the ULs and the VLs are shared across the whole graph?
The what?
The ULs and the VLs?
Yes, yes, they are shared. Absolutely, yeah.
The eta is basically local, right? So
yeah, but this is also shared. So this A, B, V, and U, they are shared across the graph. They are completely independent on the location of the graph. You just share this information across the graph.
because it's a specific way you construct them.
Yes, absolutely. And it's very important because you don't want to have too much parameters. Yes?
Yeah, so molecules are in three-dimensional space,
Yes.
aren't they? So how do you represent these relations, the spatial relations?
So your H here, this is like feature, okay? So at the first layer, the feature is going to be your 3D coordinates, for example. And then they are going to be processed, at each layer in a different way to make the best possible representation to solve any task. But it's really at the beginning, at the first layer, that you give everything you know about your problem. So like the 3D coordinates.
Pythagoras' theorem.
Huh?
Pythagoras' theorem. We know how objects are related in three-dimensional space by Pythagoras' theorem.
So you may use this you may use this property.
Where?
So I don't know how, if it is like a relationship, it will be on the edge, for example, like a distance, like an energy. It's something that is really tailored to your specific application. So we need to discuss that, because I don't know exactly what it is.
I think the question is not arbitrary lengths are actually lengths of something in 3D. So how do you put the constraint represented that something does come from a three-dimensional shape or a three-dimensional set of points?
But what feature? Are you talking about the coordinates?
Yeah.
The coordinates are here. This is the coordinates. So at the first layer, let's say this is your first layer, your input layer. So you're going to have a feature for this atom. And you may have the 3D coordinate of the atom. You may have also the type of the atom and other features. But everything will be here. It's just your H at the layer 0 will have all the information about your system.
I think they're asking is that if there is a certain very strong relationship between the atoms, like let's say triangle inequality between the coordinates, this architecture won't respect that explicitly.
So what you need to do is to design a special layer to respect this kind of constraints. Okay. And it's fine. If they are like geometric structure, that's something you can do.
Okay.
Yeah. Yes. Okay, I am slide 7. Yes.
You've talked about properties on the edges many times, but you have nothing in your formulation with the edge property.
Yes, yeah, because it's too soon. So I'm going to have more than this. So here you have, this is a function applied on the edge. So here I didn't put any edge feature, but you can, and I will do that later. You can imagine some edge feature here, and then they will be inside, this function. They will come.
Confused because you didn't have it.
Yeah, it would just. Okay, maybe I keep going. So recent new techniques is attention networks. So people also try to extend attention to graph networks, and it's more or less the same idea of what I just showed you before. It just, the anisotropic property that we try to learn this time is more like a softmax property. So the idea is we are not interested to see the connection between vertex I and all other vertices J. We are just interested in a few of them. So we use softmax. With exponential, you're just going to focus on one or two neighbors. But basically, it is the same idea. It just is very popular now, so I'm making the connection. And what we do, so the question is, which class of neural network is the most powerful one, okay? So we try to compare different class of neural networks for two small and controlled experiments, which are subgraph matching and semi-supervised classification. So very simple, but we control everything. So the first experiment is, okay, you have a small pattern. It's a small graph, okay, and then you have feature on the vertices of the graph. And what you do is that you embed this graph into a larger one, okay? And you want to be able to identify this graph. So in some sense, this is the most basic, pattern matching, graph pattern matching problem, what to find, common feature across big graphs. So the same also for semi-supervised clustering. So we have a graph which is basically community graph. So you may have, different graph, and the only thing that you know is for each community, we know one member. Okay, so this is member of this community 0, member of this community 1, member of community 2. Okay, and then you want to be able to infer all the other members of the community. So it's a very standard, problem for Facebook if you want to identify, same communities. And then what we observe is basically the performance of graph ConvNet is better than the performance of graph recurrent neural network. And the thing is, it comes from when you want to stack many layers. So what we know in deep learning is that the deep is basically stacking many layers. And the more you can stack, the better, the performance will be much better. So what happened with an RNN, recurrent neural network, is that if you stack too much, then the performance starts, to decrease. And we know that for some time. But if you stack convolutional layers, then the performance is monotonously, increasing. So the same also for the computational time. It takes less time, than recurrent neural network because we don't have to solve the fixed point iterative problem. And also we learn much faster. So this is the accuracy. So if you don't know which one to use between a graph recurrent neural network and a graph convolutional neural network, you should use a graph convolutional neural network. That's the conclusion.
Is the generalization accuracy there? Is this test accuracy? Generalization accuracy?
It's a generalization. It's test accuracy.
So at some point, does it start to come down, or is it?
No. It's monotonous. So here you have a special property that we call skip connection. A skip connection is basically the idea you diffuse the information, and sometimes you don't need some layer. Basically, you have a skip connection that will not use this layer, and you will not degrade. It's basically you are stacking too much. You don't need as much capacity, but it's fine. It's not going to degrade your performance, which is not the case with LSTM and recurrent neural network. Yes?
Is the tension in all of these convolutional neural networks? I guess I don't understand what the you have 5 plots here. Could you tell us what the difference between them is? We have 5 lines in your plot here.
I have 5 lines. Oh yeah, just because I compare, different kind of convolutional neural networks and different kind of recurrent neural network. So the dashed curves are basically recurrent neural network, and the solid lines are convolutional neural networks.
Did you find a conclusion about if attention mattered at all in your simple tasks?
For attention?
Yeah.
So attention is like a convolutional neural network that's the same. So basically, they work much better than a recurrent neural network.
Okay.
Yeah, that's the conclusion. I mean, you don't need to hesitate. Just take a graph convolutional neural networks. Yes?
What is that arrow in the plot?
What is this? Oh, this is the number of layers. Number of layers. So you know the performance of a learning system is going to get better if you stack more and more layers. The question is, how many layers do you need? And the problem is, I don't want to care about the number of layers. So I want to stack as many layers as I want, and I don't want the performance to degrade. And this is what happened with RNN.
With too many layers, accuracy actually drops.
Yeah, because this is the problem with an RNN. The system is too complex to learn. And because it is too complex to learn, at some point, you have too much nonlinearity and you degrade your performance, which is not the case with the ConvNet.
Well, you have this historic thing with regularization.
Regularization, I don't have any specific regularization except stochastic gradient descent, which is powerful enough. All right. So, what time do I have? It's related to the question I was saying before. In a graph, you don't have any notion of directions, right? Up, down, left, and right. You don't have this. So you want this kind of anisotropic property, and again, you can get it if you use a gating mechanism or attention mechanism, or either is you already have this kind of type for the edge connection, like the bond in molecules. Okay. So molecule generation. So my goal here is to design a neural network that can auto-encode molecules, okay, create new molecules, and produce molecules with optimized chemical property. So this is what I want to do. For this, I'm going to design a graph autoencoder architecture. So I'm going to have a graph-to-graph model. And of course, it's going to have two parts. The first part, I'm going to do the encoding. Okay, so I'm going to start with my molecular graph. Then with the encoder, I'm going to have a continuous vectorial representation of my combinatorial graph. Okay, so this is the first part. This is the encoder. And of course, what I want is that I want a continuous representation of my molecule in such a way that if I have two input molecules that are close to each other, I want them to be also close to each other in the continuous space. Okay, that's the idea. Okay, so once I have the continuous representation of the molecule, I want to decode it. Okay, so I want to use a decoder in such a way that I'm going back from the continuous space to the combinatorial space. So this is the decoding part. So you know in deep learning, we have already this idea data to vec and vec to data. Here data is the graph. So we have graph to vec and then vec to graph. So let's look at the first part, the graph encoder. So graph neural network, already been used to encode, a molecular graph in a vectorial space, in a continuous vectorial space. So there are some great papers about this. So like Juvno, there is also speakers at this conference, Gomez, Bonbarelli, and also Alan Aspuru-Guzik. There is also the paper by Gilmer and another speaker at this conference, Relay. So they will probably talk about this. And they will basically do a regression problem. So the input is a graph, and the output is a scalar. It's a regression problem. And what they show is basically you can really speed up a lot, this computation. And the idea is basically doing two equations. The first one is, I'm taking my molecule, and what I'm going to do is that I'm going to embed each atom of the molecule. Okay, so let's say this is atom I, the blue point, and to do the embedding, I'm going to use the neighborhood of these atoms, so the red points here. Okay, so I have a function that I apply on this. I can take my favorite graph neural network, like graph attention, graph recurrent neural network, graph ConvNet. You can take the one you like, and then so I have an embedding for each atom. Then I need to have a sort of aggregation, some reduction function. So what I can do, of course, the sum over all these features. Or what I can do, I can also take the mean, or the weighted mean, or the max. I mean, very simple operation that you can think about. So that's, in some sense, doing graph encoding is easy. And what is really challenging is to do the decoding. Going back from the vector to the graph is really challenging to do. So today, there are like two kind of approaches to do that. So the first one is autoregressive models. So the idea is to reconstruct the molecule atom by atom and bound by bound. Okay, so for example, here is an illustration. So there are two important papers, so Jean and their co-author, and you, Leskovec, and their co-author. So you are at this level of reconstruction. You need to decide what is the next atom. So for example, the next atom is the carbon, and also you need to decide what will be the bound, the type between this atom, and you keep going. Okay. The other alternative is to do a one-shot model. So in this situation, you will learn all atoms and all bonds simultaneously. So there are papers, Simonovsky, Komodakis, Dikau is a speaker at this conference, and Thomas Kiff. And the idea, okay, is to learn everything at the same time. Yes? In the sense it's easy, I should put it, like this. So in the sense that going from a combinatorial object to, a vector is kind of easy. But you take your vector and you decode to a graph. This is much more difficult.
You don't know whether it's a proper way of encoding that.
Oh, yeah, of course, you need some kind of criterion to say that. So in my world, this is something easy. And of course, you need to put additional constraint, like physical constraint, this kind of stuff. But I think still it's reasonably easier to do than doing the decoding.
So I'd expect because the inputs and the outputs lie in the same space, isn't there some sort of symmetry that you can argue?
Yes,
between the decoder and
you could do that, like bijectivity. So for example, you can learn, and we come back to that, but the encoder and the decoder substance should be symmetric. Yeah. There should be some symmetry between both. Some people do that. Yeah, but usually from the machine learning point of view, it's not going to change much. Because the thing with deep learning is that you don't really care about the weights that you learn.
Right.
Because it's a very high-dimensional problem. So each time you run your algorithm, you will get a different weight values.
Yeah, but wouldn't it be, just in terms of the machine learning, would it be helpful to reduce the search space? Right, because you have so many parameters.
Yeah, and exactly, and this is what we try to do with architecture. We try to find the minimum, inner structure. So the minimum number of parameters you need to learn. That will give you, the good results. If you have too much parameters, then first probably you will overfit and you will not generalize. And the second one, you will not capture, the property of your data. So that's the game. The game is to try to find the minimum set of inner structures. If you can do that, then it means you understand your data, you understand your task. And here it's already it's too much generic, I would say.
Is it sequential generations of molecules? When you say atom by atom, you mean like literally sequentially in space?
Yes, so sequentially in terms of atoms. So you are at this stage, and then you want to know what is the next atom, okay? And then what is the bound, okay?
So I presume those kinds of would be difficult because you could have errors, an error early on in the generation process could accumulate to mess up the whole rest of the molecule.
Absolutely, exactly. If you make one mistake, at some stage, you will not be able to correct the mistake. Absolutely, you're right, yeah.
Depends on the model. Some models can go back and they take away things they did earlier. Depends, details of how you construct.
Yeah, but it's not easy to do. Most techniques developed, they don't really do that. It would take too much time. But yeah, you can always go back. But in this situation, I would say it's better to have like the single shot approach, because it's more general. So you can always modify what you have.
And if the decoder has to backtrack, then backpropagating through the decoder might be quite difficult.
No, it's fine.
Not harder than the first case. You have more actions to do, and so that's kind of a problem, but the conceptually works.
Yeah, absolutely. Even if you go back and you change something, you can always use backpropagation. The thing is, you need to start again. So everything that you have done so far, you need to start again. But backpropagation will always work. Okay. So one challenge when you use a single-shot, decoder, is to solve these three problems at the same time. So you need to know what is the number of atoms, the atoms, and the bond structure between the atoms. So the way this problem was solved is basically, okay, let's generate molecules with a fixed size. So basically, the fixed size is going to be the largest, molecule size in your training set. And what we propose is an alternative to that. So we propose to disentangle these three problems by doing these two operations. So we're going to use the molecule representation, okay? And then from that, we are going to do atom generation and bond generation. So the atom generation is basically, we want to know what is the molecule formula. Okay, so we have some molecule, and what we want to know is what is the histogram of atoms inside the molecule. So if you sum over the histogram, you will have the number of atoms in your molecule. Okay, and given this molecular formula, then also using the molecule representation, we will use these two together to basically infer the connection between the atoms. So this is what we propose. So the atom decoder is easy to do. The input is going to be the continuous representation of the molecule. Okay, so it's a vector of fixed size, and the output is going to be the histogram of the atom. So it's also a vector of fixed size. So when everything is fixed, you can use an MLP. So this is exactly what we did. So for example, if we have this molecule with 3 atoms of carbon, so you will have an histogram with 3, and 1 atom of oxygen, just 1. Okay, so we have this bag of atoms. And then we do the bond decoder. So this is like an IKEA model. So the bag of atoms, the molecular formula, it gives you all atoms inside your molecule, okay? But you don't have any order. You don't know anything about how you do that. So this is your IKEA pieces. And then you need, an assembly instruction. How do you put the atoms together to form a molecule? So for this, we are going to use a graph neural network. So the input of a graph neural network is going to be our bag of atoms and the molecule representation. Okay, we're going to use these two inputs, and the output will be a graph. Okay, the molecular graph.
Question. So when you said that you have a representation of the molecule, what part do you exactly put right here?
Sorry?
The meta representation. So what do you put in right here?
So what we will have all the atoms inside the molecule. And what we have here, this is the guide, and the guide is basically, the vectorial representation of the molecule. So during learning, what happened is that we will tell the system, okay, you need to summarize the molecule inside one vector, and this one vector should also give you the instruction, to assemble together all the atoms.
Right. So right now they might be like a mass or a charge or like.
What is that?
Yeah, or just like different vectors.
Yeah, different vectors depending on different molecules, different atoms, different bonds. It's like a summarization of your molecule inside one continuous vector.
But this is the output of the encoder, right?
Exactly, this is the output on the encoder.
Whether you directly put in actual molecular properties like position.
Yeah, but it's already, when you do the encoding, your input, you're going to have, 3D coordinates, atom type, bond time, everything. And then everything will be summarized here.
No, I think he's asking whether it's going to be something human interpretable or it could be just some.
That's a good question.
It's going to be some highly difficult to interpret abstract thing.
Yeah, I think it's going to be hard to interpret. And the more inputs you put, the more difficult it's going to be to interpret. So looking at the latent space of representation, I can make nice drawing, but at the end I'm not sure it's something useful. Yeah. Yeah. So maybe we can come back to that later. Okay. So when you use the single shot decoder, because you reconstruct all atoms, all bonds at the same times, you may not create valid molecules. And basically, the problem is going to be that you are going to violate the atom valency, okay, the maximum number of electrons in the outer shell. So what we do to fix this problem, we use a standard beam search technique, which is used all the time in NLP. So in NLP, when we do translation, the decoder is never able to give us, a right, sequence B. So in translation, you go from sequence A to sequence B, but the sequence B must make, some sense. And usually you don't have a lot of sense. So the way you get sense is basically using a beam search decoder. So we do the same for molecule. And it's very easy. So you start with a random age. So let's say this is my molecule, the output of my molecule after decoding. So what happens is that for each edge, I will have a probability distribution over the bond types. Okay, so I here for this edge, the neural network say, okay, there is 45% that this is a single bond, 25% it's a double bond, 5% aromatic bond, and 50% there is no bond. Okay, this is the output of my neural network. And then I'm going to use that to reconstruct the molecule. So I start with a random age. For example, let's say I take this one, and then I will select the next age such that I will have, I will take the largest probability, so maybe this one, or I can do also Bernoulli sampling, right? I can roll the dice. And then I'm going to connect with some existing selected ages. Okay, so it already exists, so I can take this one because it's connected. And of course, I do not want to violate the valency. If I violate the valency, so I will use another bond or maybe none. Okay, so I repeat that for different initialization, and at the end I will select the molecule that's maximizing the product of edge probability of edges. Or maybe the chemical property, like for example, drug likeness or constraint solubility. So that's very standard in NLP, and I'm just using that for molecules. So in summary, okay, I start with my molecular graph. I use an encoder with graph neural network. I get a vectorial representation of my molecule. Then I'm using an MLP to get the atoms inside my molecule. And then I'm using the atoms and the molecular representation together to get the edge probability matrix. I do beam search on that, and I get a valid output molecule. Okay. How much time do I have?
So, time slot, including discussion, ends at 11:25.
Oh, okay, thank you. Okay, it's more than I need. Okay. Okay, if I give you a little more details about the encoder description, so going from the molecular graph to the vector, so again, I'm going to embed each atom inside my molecule. So again, I'm going to use my diffusion operations on graph, which is very generic today, so it would be nice to make it more specific with some physics. Here I'm using a dense attention. Now in the community, in the deep learning community, there is a lot of discussion about attention network. So here we are not using sparse attention like the community is using. We are using dense attention. The idea is that one atom may communicate with much more with a lot of other atoms. So we get better results. It's not really clear why, but yeah. And then we also do a bond, embedding, bond representation. Between the atoms. So we don't really know what to put here. Again, it would be nice to have some physics property. So we just put the edge at the previous layer, and also the atom embeddings from the starting node and the ending node of the edge. Then at the end we have the graph representation. So we just do a weighted sum. Okay, we just sum over all the edge, all the bond representation, and we get, the representation of the molecule, the continuous representation of the molecule. Okay. Yes.
Can you repeat your point about the dense attention, please?
For the attention, yeah. So the thing is, so you want. So in some sense, you want to know which atom is going. For this atom, what are the other atoms that are important to be connected? Okay, and in some sense, I want the system to learn by itself. I don't want to tell beforehand, okay, for this atom you should connect with the other atoms. Okay, I want the system to be able to learn by itself. So this will basically try to learn. So there are some parameters here. So you see you have some parameters here. So the system will try to learn for these molecules, this atom should be connected to the other atoms. Now the question is what kind of attention you're going to do. If you do a sparse attention, it means that one atom will only be connected to one or two other atoms. If this is a sparse attention. If here you take exponential of this, sum over the exponential. So it's a very sparse attention. You just connect one or two. Or here what I do is a dense attention. So there is no exponential. So basically you have a chance that this atom is going to be connected to maybe 3, 5, 10 other atoms.
So this is my question then. This is a fully connected molecular graph.
Yes, it is.
Every atom is connected to every
yes,
other atom in the molecule.
Absolutely.
Okay. But that's not how typical, maybe people would think about molecular graphs. I think most people would maybe think about bonds.
Think about?
Bonds. That your graph walks through the bond, right?
Yeah. So yeah.
So localized version.
It's a. Do you want a sparse graph, something like that?
That's. I think most people in the audience might have been. I was thinking that you were connecting, following the chemical bonds in the graph.
Okay, good. We should talk. That's very interesting. Okay. Any other questions?
Is this a good place to plug in prior knowledge that folks have about?
That would be good, maybe. Yes, absolutely. So this is very generic, but maybe you can add a matrix Aij that will, give some domain expertise. Absolutely, yes. That would be very interesting. Yeah. Any structure we can put inside the network would be nice. Yeah, absolutely. Okay, so now for the bond decoding during training. So during training, so we have our molecular graph. The molecular graph is going to give us encoding. So we will get the continuous vector, and also we will get the bag of atoms. We will know that for sure. And then we use that to compute the edge probability matrix. So yes, it's a dense graph. Okay, it's a fully connected graph, and for each connection. You have a probability that this is like no connection, or maybe you have this connection.
So, could it be a problem, or is it possible that this is not unique? That going from left to right, there might be multiple solutions?
Yes, usually you have multiple solutions. So, and then you have the problem of matching. So we have a way to fix this problem here. Yes, absolutely, this is a big problem. So for one input graph, you may have multiple, output graph, which have the nice, the same loss, basically. Yes. So yeah, I'm coming back. So, yes.
How do you have the different molecule sizes in this matrix? Is it fixed from the beginning?
So the size is going to be given by this. So here, if you sum over the histogram, you will have the size of your molecule. And then here, so for example, you have 1 plus 2 plus 3 is 6. So you will have here 6 by 6. This is how it is done. Yeah, okay. Okay, so at test time, we don't know, the input graph. We don't know the input molecular graph. What we know is basically we are going to play in the latent space, in the continuous space. We are going just to move around this space. And then we are going to use that with an MLP to give us, the molecular formula. And then we put everything together and we get the edge probability matrix. So this is at test time. Okay, so there is an issue with this. The problem is, let's say, for example, my molecular formula, I have 3 atoms of carbon, 2 atoms of nitrogen, and 1 atom of oxygen. Okay. So the way I decode, basically, I start with a fully connected graph, right? Any atom is connected to all the other atoms. This is how it is. Okay. So the problem is, how can I differentiate this atom of carbon, this atom of carbon, and this atom of carbon here? Okay. The neural network will not be able to differentiate these three atoms because they have the same type. So it will never work. Okay? The same also for the nitrogen. We don't know that. So we need to add some additional information to differentiate atoms of the same type. So for this, we are going to introduce positional features. So the input is going to be the type of atom, and then we're going to have a positional feature. So how do we get the positional feature? So basically it's a sense of what is the order of the atom inside the molecule. So it's a very hard problem. We don't have a nice solution. We just use the SMILE representation of the molecule. So the SMILE representation of the molecule, so you have your molecule. The SMILE representation is a string of characters, okay, representing the molecule, and it's a lot of good information from chemistry. And what we do is that, okay, our positional value will be, so if this is the first atom of fluor, we put 1. If this is the second atom of fluor, we put 2. Okay, so this is how we fix this problem, which is not completely satisfying, but this is what we did. All right. Then we use variational autoencoder, because you know that if you use an autoencoder, you will have the problem of mode collapsing. Basically, the space that you're going to use is going to be probably empty, and there will only be, information around your training point. So you want to fill up the space. The way you fill up the space, you need to regularize. So one way to regularize is to parameterize your molecule, your continuous molecule representation by some Gaussian, some Gaussian distribution. So you have the mean that you will learn. Okay, so this is going to be a neural network to learn this guy. You will have the standard deviation, so you will also use a neural network. And then here, this is just the normal distribution. Okay, you have the normal distribution. And okay, and that's it. The rest is going to be exactly the same. Okay, we have our continuous representation of the molecule. We can get the molecular formula. We can use the decoder, and then we form the molecular graph. The loss, so basically, we will have, actually I forgot one term. So the first term is going to be a cross-entropy loss for the edge probability. So we know for each edge what should be the ground truth, right? The same also for the bag of atoms, so the molecular graph, we know that. We have also the Kullback-Leibler divergence for the Gaussian distribution. And then we also have another one. So if we want to learn an embedding space for this molecule associated with this property, like energy, then you will have another, a term like L2 loss on this, on this energy. For example, you want to encode, you want to represent. So we don't have matching to do because we have the same ordering for the atoms for the input graph and the output graph.
So I mean that's a little bit misleading though, because that's true.
Which one?
The last statement, because it's true if the input and the output are exactly the same, then the matching will work out. But in a SMILE's representation, I can change any atom, and that can completely reorder everything. And so you're not actually getting the minimal matching here. You're just picking whatever happens to come out through your SMILE's canonicalization.
And I agree with that. I completely agree with that. We don't have a satisfying solution. I agree. So exactly what you said. I mean, there may be different, reorganization of your atoms, and you get the same energy. So the thing is, the problem for us was breaking the symmetry of having, the same, having atoms, having a multiple number of the same atoms. So we use SMILE to break this symmetry, and at the same time, it really, fix the problem of the matching. But there may be, multiple, inputs and multiple outputs that will give you exactly the same loss. So it's not satisfying. I completely agree with that. But yeah, this is something we need to work out.
Can you speculate about using other instead of the SMILE feature representation? Can you speculate about?
Yeah, exactly. So in some sense, exactly, you should. But even that, I mean, you will not solve this problem. The problem of matching by, you want your matching process to be independent with respect to the, reparametrization of your molecule in some sense. And that's very hard. That's very, very hard to do. Yeah. So it's just one trick here to make it work. Okay, the data set, so we use zinc. So it's a 250,000,000 of drug-like molecules. So you have, up to 38 heavy atoms. So this is the histogram of the zinc molecules. Okay. So we use mini batch of 50 molecules. We have the learning rate schedule. We decrease, by this factor every epoch if the training loss doesn't decrease much. And we stop when the learning rate is basically very small. Okay, and it takes 24 hours on one GPU to do that. And the numerical experiments we do, so they are very standard. So we do molecule reconstruction. So how many molecules are correctly decoded? Molecule novelty. So we sample from the distribution how many new molecules we get. And we do molecule optimization. So we stay in the latent space. We move in the latent space in such a way that we increase property value. And this is what we did. So we compare with so the GT-VAE paper from MIT with Jean, which is basically VAE plus supervised learning plus autoregressive, and also the paper by Yu and Leskovic, which is GAN plus reinforcement learning plus autoregressive. So the two papers are basically SOTA. For the molecular reconstruction, so this is your reconstruction rate, so the higher the better, and this is the validity of your reconstruction. So GT-VAE was the previous state of the art, 76, 100% validity, and now we get to 90% by using the technique and 100% of validity. So we are happy, we increase by more than 10%. For the molecule novelty, so we sample 5,000 molecules, okay, from the prior distribution, and we get 100% new molecules, and these molecules are all unique. Okay, they are not the same. Okay, so then we do like molecular optimization. So the idea is now we stay in the latent space, okay, and then we are going to move in the latent space in the direction, in the ascent direction, in such a way that we will improve chemical property, okay, which is here the constraint solubility, okay, and then so we move inside this space, the latent space, and then we decode. We have a molecule, and we compute, property of this decoding molecule. And this is what we report. We report here the top 3 optimized molecules. So GT-VAE was doing in mean 4.9. We get a little more, 5.1. And if we use the work by Yu and Leskovic, so they get much more. And it's interesting to look at what they get.
How do you compute the constraint? How do you compute the property?
So the probability is a constraint solubility. So we use RDKit to do that. It's automatic. Yes?
How do you determine the direction to move in the latent space of the
Okay, so we are just going to move. So the space, the latent space, is parameterized by your property. The property, like for example, solubility, is one parameterization of your loss. Okay, so what you're going to do is that you can compute the loss, the gradient of the loss, with respect to your property. So you just go in the direction where the property is going to increase. So that's easy to do. Okay, and so what you see is very interesting. So these two techniques, so this is our technique, this is the technique, the GT-VAE, they more or less produce the same, statistics of molecules. And it makes sense because we are using, VAE. VAE, variational auto-encoder, will only give you output of the same statistics. And we can see that. But if you use reinforcement learning, with reinforcement learning, you can get outside the statistics of your training data. And you can see that, this is not part of the training set. So of course, our goal is to go to reinforcement learning next step, yeah.
It's maybe not a question to ask you, but just in general, to me, it doesn't make any sense to optimize this like optimal water solubility measure because like once you're above a certain level of solubility, being more soluble doesn't make you more likely to be a drug.
Yeah. Again.
Build the whole field where everything focuses on this one metric. Like it seems like maybe overstating the ability of these techniques to solve the problem, given that the problem you have is so ill-suited to the thing which you actually would be investigating in like a pharmaceutical company.
Yeah. So again, I'm
because just keeping adding carbon atoms on.
Yes, exactly. Yeah.
And so this is actually like if you told me to optimize this, I would just keep drawing little carbon shapes.
Exactly.
So yes, it's terrible.
Absolutely. So I think my point here is not trying. I'm not an expert in computational chemistry. I'm not at all. What I want to open here is more like a collaboration with people. Say, okay, you know what kind of objective we should optimize, what kind of property constraint we should put inside. Let's work together to get the best possible molecule generation stuff. Again, that's why I started saying I'm not an expert. I'm just we have tools. New tools that we may use, for the field, finding like a common ground. But I don't say that this is going to be, the final solution at all. And finally, the final. I'm sorry.
So in the previous slide, you were comparing so auto-encoders versus GANs, right?
Yes.
The main difference is GANs has a much powerful latent space because it doesn't assume a form of distribution. You can actually incorporate that in auto-encoders by using something like normalizing flows to improve your OCR distribution. Right? So assuming Gaussianity, you could improve the complexity by using normalizing flows per se, and it could get close to GANs.
I don't think here the thing. It's not GAN that makes the result better. It's not GAN versus VAE. It's not. GAN, again, will not be able to get outside the training statistics. It will not be able to do that. GAN is just a generative model, like VAE. It is better to generate data than VAE, for sure, but it will not be able to create new statistics. What is able to create new statistics is reinforcement learning. So we are in the same. So VAE plus supervised learning, GAN plus supervised learning will give you more or less the same result. With GAN, you will get better results, we know that. But if you want to get, this crazy stuff, you need reinforcement learning that is able to create, new strategies, new policies to get outside the training set that you have. It's more reinforcement learning, which is here the key.
But it sounds like what the discussion is saying, that the reinforcement learning, although it optimized this particular metric better, it did it in a kind of,
Yes, just by putting more, exactly, yeah. It found actually that this is what we need to do, just, to increase this property.
So it somehow it was able to better optimize the objective, but this just says that the objective is
bad.
Incomplete.
Yeah, exactly. It's not enough to make, valid molecules, absolutely. But you see the power. You see that you can get beyond the training statistics. So if you have the right, physical laws, all the nice properties, you can create new molecules that are, that's a promise. The second optimization is to, let's take, molecules in the test set that we have never seen before, and let's try again, to improve their chemical property. But at the same time, we want, to measure the distance between the molecule and the new molecule. Okay, so you start from an original molecule, then you generate a new molecule, and you want to compute the distance between both. And you want to create new molecules that are not too far away from the original molecule. And the distance is the way to control, how far you're going to be. So this is GTVAE, so this is the chemical improvement. This is the similarity between your original molecule and your new molecule, and this is the success rate if you're able to create a new molecule. So if you use, so this is GTVAE. If you use GCPN, so this is what you get, and this is our model. So what you see is that our model gets better, chemical improvement than the previous ones, but we don't have the same success rate. Here it's 100%. So in some sense, we can compete with reinforcement learning here because we force, the molecules to be close to the original one. So if you force, your molecule to be close to the original one, so VAE is still, doing a good job because you stay in the range of the statistics that you train on. If you use reinforcement learning, you can go much beyond, but here you force your system to stay close to the statistics that you train on. So yeah, this is what you get. So just for fun, we did some visualization. So if we want, a close similarity, we start with this original molecule. Then we optimize to get this one. So it's just here going to cut. Here we start with this one. It's just going to change this part of the molecule, and we get this one. okay, conclusion. So we propose actually something which is very simple, VAE. So you see that there are not too much chemical constraints. The only two things that we have, we use the smile. We use the smile, and we also use the valency. Okay, we want to respect the valency, and okay, so we get some compared to the state-of-the-art literature. So we get more or less, we get sometimes better. And the conclusion of this is, if you look at the papers today, try to do molecule generation. Most of the papers they do it in an autoregressive way. Okay, most papers they do that. They just do atom by atom, bond by bond. So what we want to advocate here is like a new direction in some sense. It's not new because people already did that, but it's something that we should more pursue. Is that if we try to solve the problem in a single shot, okay, and also we use beam search, these two can be highly parallelized. So you can generate a lot of molecules, and you can you can be much faster than autoregressive. So next step is going to RL, and we also our technique is very interesting because we can do large molecules. Once you fix the size of your molecule, and you will do that because you fix the molecular formula, then you can use hierarchical representation. And hierarchical representation just means that you can represent n atoms by using log n layer. Okay, so you can think that this technique can really scale to large number of atoms. So that's something interesting. And of course, for me, I really want to use this opportunity of this week is to discuss with you, with experts to see where we can go from here. Because for me, it's really new work. So thank you very much for your attention.